Hello.
Hey, hi, Janice.
Hey, cool. Great to have you here. Hi, everyone. Welcome to Google Developer Space channel, and thank you for tuning in to our very first collaboration with the Data Science Singapore community. As you know, we're a platform for developers and startups from around the region to learn, connect, engage, and be inspired. Last year, we welcomed over 15,000 developers in person at our 180 events here in Singapore. And despite the unfortunate circumstances that we're in right now, we want to continually empower and connect our developer community to our people, program, network, and technologies. So tonight, we're super excited. We have Singapore's largest community, a developer community here with us, DataScience SG, led by Ku, of course. And thank you, Ku, for bringing such a great a great speaker to us tonight. And it's super appropriate. The weather has been going crazy, so I'm super excited to hear how Arnold is going to talk to us about predicting weather. I think we all need that, no?
Yeah, correct. And thanks, Janice, for having us on Google Developer Space. How are things with yours?
We're good, right? We've done 2 events, and actually we've got like 6 more lined out. So you should all stay tuned to see what are some of the upcoming events. You can join follow our social media, join our newsletter, and of course, Data Science SG. I think they have 3 events in the coming month. And we'll be hosting here as well on our channel. So do check in again. And if you miss it, don't worry. They're all recorded. They're on our YouTube channel. So you can always check back in later.
Yeah. Okay. Anyway, good evening, everyone. Thank you very much for coming. For joining us on the YouTube platform. I'm still so used to the physical meetup. Welcome everyone. I also understand that I've actually may have guests from Indonesia, Bangkok, Taiwan, Malaysia as well. So welcome if you're from those countries. Again, thank you very much for spending time with us. Okay, so what's next?
I think we've got Arnold waiting backstage, so let's bring him on board.
Yes, let's bring Arnold on board.
Hey, Arnold, great to have you here with us. Really looking forward to your session. I'm going to jump backstage and let you take center stage.
Okay.
Hi, guys.
Hi, Arnold. How are you?
Fine, thank you. Just stuck in home for the last 3 weeks now.
Don't tell me about it. I really cannot remember how many days I spent at home really. Yeah. So anyway, thank you very much for agreeing to speak to our community and share with us how to do weather prediction. And also, I think it's a software that we probably haven't heard much about it, and that's AutoCAV as well, right?
Yes. Although we're not doing weather prediction today, a bit of weather prediction, but it's only quite general for forecasting.
Okay, I think without much further ado, let me hand the time over to you then.
Okay, so let me just introduce perhaps. Yes, but so today's topic is all about using neural networks specifically for forecasting, and I'll go through some perhaps less known tips and tricks that you might find useful. So I will assume that you already are familiar with actually training your own models, doing that kind of stuff, and also familiar with neural networks already. So I won't cover that too much. Okay, let me just introduce AI4IMPACT a bit. So our mission is really all about trying to make AI accessible to non-programmers. And since 2017, we have trained about 1,000 over people in AI. Okay, my name is Arnold. I have a background in physics, and of course, I've been a weather forecaster for about 20 plus years. I've been dabbling in AI since the 1990s, and I still consider myself very much a student. Okay, so before we start, I want to just cover 5 basic concepts when it comes to forecasting. Well, the first one is about lead time. So lead time is how much into the future you want to do the weather the forecast. It could be like 30 days ahead, 30 minutes ahead, sometimes even perhaps 10 minutes ahead, right? It's useful. So we use a T plus notation. So T plus, let's say 5 means T plus 5 days, T plus 30 minutes means 30 minutes equal like T plus, can be like 30 minutes ahead, right? So we use the T plus notation, and T plus 0 means the present. So if you look at this graph of temperatures in Singapore over the last few years, let's say this red dot represents the present, okay? So this yellow dot is, let's say, 180 days from the present. That'll be T plus 180, okay? Very easy. Now, measuring accuracy of your forecast, I'm sure all of you know about RMSE and, of course, the MAE as well. So I won't cover that too much. But the important thing is that to understand that, and I hope you will see this very clearly in this presentation, is that single numbers always will miss out some valuable information about what you're trying to do. And this is especially true for time series forecasting because it involves an element of time. Okay, and we'll see also that sometimes local loss functions are not very, like RMSE, etc., are not very good for time series predictions. Okay, the third concept I want to introduce is this thing called persistence. So when you're doing a forecast, you can say, you can ask me, Arnold, what is the stock or market price for, let's say, Apple stock 1 week ahead of time from now? So T plus 7 days, right? And if I say that the future value, the predicted value, is the same as what you have right now, that's called a persistence forecast. So if, let's say, for example, you ask me, so what's a T plus 7 forecast, Arnold? I say, well, what's the value today, right? It's $30 or let's say $100, right? So that would be my forecast. So that's called a persistence forecast. So in other words, T plus some X is the same as T0. It's a definition of a persistence forecast. And what we do is, it's a very simple forecast. It's a useful benchmark, and we start with that. Now, persistence is easy to beat, obviously, for long lead times. For example, let's say you ask for a forecast of stock price, let's say 1 year ahead of time. Persistence is a bad forecast for that. But persistence is actually very hard to beat for very short lead times, and especially if the thing you're trying to forecast doesn't change very much. Okay? So any credible forecast must beat persistence. Now, each field that you go to with to do any kind of forecast, whether it's like a demand forecasting or let's say failure prediction or let's say earthquake prediction, etc., they will all have some kind of benchmarks relative to that industry. And persistence is a general benchmark which pretty much you must use. Okay. Now, the fourth concept, is the concept of lag. Okay. So if you look at this graph here, you can see two graphs. The blue line represents the actuals. So time goes from left to right. Okay. So the blue is the actuals, and the orange line are your model predictions. And you see that, they look pretty much the same. Okay. Now it's obvious that what's happening here is that the prediction are just a copy of the actuals and shifted forward in time. In other words, it is actually a persistence forecast. And so the question is a prediction like this useful? And the answer is perhaps not, or it might depend really on your application, right? So how do we measure lag easily? Well, a simple method is to use something called a lag correlation. So I'm sure most of you are familiar with correlations. So a lag correlation is where we keep, so the Y cap here represents the forecast, and the Y represents the actuals. So what we do is we take the actuals and we lag them maybe backward in time, so that's a delta minus something, or forward in time, a delta plus something, and we calculate the correlation coefficient in this case. Okay. We can normally in the normal case we would actually normalize by the SDs of both the forecast and the model and the actual values. But here, so this is the kind of graphs you would get. Okay, so when you do something like this, you probably get a single major peak, or sometimes multiple peaks, and where you get the peak occurring, that delta, that shift measures the lag. So if I go back, for example, here with this thing here, the distance between the peaks, between these two, between the actual and the predictions would be your lag. So, and that would manifest itself here as your 5. Okay. All right. So lag is 5 units with 5 days, 5 minutes, 5 seconds, who knows? Okay. And here you got two models here, model A and model B, and obviously the lag for model B is a lot better than model A. And so one of the goals that we have in forecasting is not just to look at the RMSE or the just errors, but also to look at lag and see whether they can be improved or not. Okay. All right. So pro tips: the first thing you got to do when you do forecasting with neural nets for time series forecasting is to try and create a forecast with a low RMSE or low error, basically, right? And this should beat persistence. And the next step, if you can, is to tackle the idea of lag. And it's always easier to actually reduce RMSE than it is to reduce lag. Okay, and sharp correlation peaks are the best, and they indicate a high confidence in your results. Okay, the last concept I want to introduce is the concept of windowing. So the neural networks, I'm not talking about, for today's talk, we won't be doing recurrent networks, just simple feed-forward networks. So these feed-forward networks require a window of data to be received and as input. So what we do is we want to take a window selection of past data as input. It's a fixed length, and you basically just move this window forward in time to generate the inputs into the model for both training and for testing. So let me give you an example. It's not so clear. So let's say we've got this time series, right? It can be not just one time series, maybe multiple time series. It would just pick, let's say, a fixed window size. In this case, I picked a window of 18 months. And that's my T0, that's my present value. I'll obviously also include that as input into the models. And that's the back part of the window, it's T minus 540. And maybe if I'm trying to forecast for T plus 180, that would be the value up there, right? So what I do is, I would take this data and I'll window it. In other words, I'll get the 18-month window, which is a big vector, and I have one output. So typically for forecasting, you really want to just forecast one thing, right? So under forecast, even for financial series, or let's say a demand, or let's say in weather forecasting, you want to build models that forecast just one thing. So in this case, I'm just forecasting the T plus 180. Now you could have multiple inputs and multiple different data sources, but you're just still forecasting just one thing. So the idea is that I will just move this window forward in time to actually generate all my training and testing data sets. Okay, so windowing basically generates the input vector and also the desired output as well. Okay, so it's just it does both things. Okay, I know this is quite fast because we have a lot of ground to cover, but cool, can we open this up for some questions now for a couple of minutes? Just to make sure everyone is on the same page. Cool, are you there?
Yes, I'm here.
All right.
Hi. So anyone has any questions, feel free to put it on the YouTube chat on the right-hand side, and for Facebook will be on the comments side. Anyone got questions? No? I think we still have a very shy group, even with the pandemic. Okay. Arnold, so why not we continue then?
Okay, cool.
Yeah.
All right. So let me just discuss the forecasting problem first. All right. So it's very simple. We've got this data for Singapore temperatures. They are weekly temperatures, and we're trying to forecast 5 weeks ahead of the present. Okay. So the way we obtain this data set is to actually just look at the different temperature gauges all around Singapore. We take a spatial average, and sometimes we even we take like a median or something like that, right? Across multiple gauges. We then average this weekly. Now we have data for about 20 years. And if you look carefully, this data is strongly cyclic. And each cycle, each up and down represents 1 year. And the cycles are caused by the monsoons and the finest. So in Singapore, you might not know this, we actually had 2 seasons. There is the northeast monsoon, which goes from, I think, October up to about April, right? So October is an intermonsoonal period, and April is also intermonsoonal. So, but during those 6 months or so, we have got the northeast monsoon. That's when you get colder air coming and blowing in from China, actually. Okay, from the Tibetan plateau, it goes across to China, and it comes in surges down to Singapore. And so you get this kind of cool weather, and that's all the dips that you see down there. But in summer, we also get the southwest monsoon, and this is much warmer air, and it also brings in the haze as well. That's when the temperatures go up sometime in June, July, August. Okay, so you can see this very strong pattern. But inside each year, there are actually a lot of fluctuations. And the fluctuations are caused by many different processes, right? There can be also things like longest, if you look at this 16, 15 plus year snapshot, you'll see there is actually a longer scale variation. And also the yearly patterns are not consistent. They might change from year to year, okay? So this is also what you would find when it comes to forecasting. Generally speaking, there are many scales of processes which contribute to the behavior of what you're trying to forecast for. Okay. Also, there are errors. Obviously, there's instrument changes over time. Singapore itself has changed, perhaps become more heat islands, etc. So it's also changed over time as well. Okay. All right. Now I will discuss how we solve this using a platform that we use in AI4IMPACT. We developed this platform. It's called AutoCAF. It's just a platform for learning AI for beginners. And we use a glue language. We don't use Python. We use something called Mojo. We've got the backend is just a modified version of Cafe 1. We use, of course, XGB, Rapids, etc., and so on. It's specifically for non-programmers, and it's be easy to use. It's a comparison. I know there are a lot of Power TensorFlow users out there, so just shout out to you guys. So TensorFlow, you have as a UI, you've got Jupyter Notebook or maybe TensorBoard, and then. So let me just give you Mojo, just an overview in a few minutes, or say 1 minute really. So this is the hello world in Mojo. So you've got in Mojo, everything is from left to right. So it's unlike Python or Java where the functions are on the left. Okay, this is left to right. So hello world is a string literal, and the dot represents a function or what we call a word that prints the literal to the screen. Okay, very simple, left to right. Okay, so in Mojo, everything is either a literal or a word. There is nothing else. There's no punctuation, and we consistently follow a left to right type syntax or postfix syntax. Okay, all right. So this is a more difficult example. So let's say you would ask to find the first 100 squares divisible by 365. Now, of course, most of you can probably know how to program this, but here's how we do it, Mojo. First, you take 1, 2, and the dot, dot, dot creates an infinite sequence, 1, 2 to infinity. All right, so that's an infinite sequence, so it's lazy. Then you square it. You square the infinite sequence, so you have 1, 4, 9, etc. And then you filter off those which are divisible by 365, and you just take the first 100 of that list, and you truncate the list, and then you print it out. The dot list prints out the list. Okay, so this is how we do stuff in Mojo. It's quite unlike Python, or let's say I'm just choosing Python. It's just an example, but most other languages will take this approach as well, like Java or whatever else you want to use. You would have a explicit loop. So the problem with explicit loops is that for beginners, at least, is that there's a lot of bookkeeping involved. You have to have the variables n and m and x, right? So that's harder for beginners to understand. And that's why we say that it's actually a beginner's language. As Mojo is a beginner's language, right? Okay, now enough of that. We'll move on to the neural networks part. Throughout this talk, I won't use fancy neurons. I'll just use the most basic one, which is called the perceptron. I think most of you know this. It's just a dot product with an input vector followed by some weights, which we call a linear combiner, okay, an LC, and followed by some theta, which is a saturator, right? It could be like a ReLU or TANH or leaky ReLU or what have a sigmoid, okay? And the important part of the saturator is that it's nonlinear, okay? All right. And we will only consider feed-forward networks. So in this case, the different perceptrons are all arrayed according to layers, layer 1, 2, 3, 4, and so on. And you always end up with a final layer for output, because the outputs from the unless you're using something like ReLU or something else, the outputs from your neurons are saturated at some stage, either on the negative side or both sides. Like ReLU is saturated on the negative side, and TANH is on both sides. So you need to have some kind of linear combiner to actually increase it. So now some pro tips for you guys. This should not be unfamiliar to most of you if you've used it. You should use at least 2 layers, not counting the final LC layer. And you want to shrink the layers, don't expand them or stay the same. And the shrinking factor should be anywhere from 2/3 to 1/2, depending on the problem that you have. And leave enough neurons at the top. I like to leave about 4 or 8 neurons at the top layer. Okay, otherwise things get a bit dicey. And if you're training in one pass, then limit the depth to about 6 or 8, I would say would be safe. Okay. All right. Discussion time again, Ku. Any questions at this stage?
Yes, we have. Hold on, let me show one of the questions out first.
Mm-hmm.
So can you see that from experience? Okay, from experience, are there scenarios where we should look at MAE instead of RMSE?
Yes, great question. So if the problem with RMSE is that it penalizes you when you are far away when the errors get larger and larger, right? So I think that when you're dealing with financial data sets, especially, you want to look at MAEs instead of RMSE. Also because in financial data sets, you often have outliers. The big problem in financial data sets is outliers. Shocks because of, price crashes or political news and so on. And so because these are so common, you want to have a loss function that is less sensitive to these outliers. Otherwise, they would dominate your learning. So yes, but for this problem, when it comes to weather forecasting, for sure there isn't a shock. We're not dealing with lots of shocks. So I would just stick with the current RMSE.
Okay, good question. We have one more question. So let me show it to the rest. Okay, let me read out to you. It's easier to get high accuracy for less than T+7 weather forecast. How about T+30 forecast? Example, predicting weather for cross-Pacific voyage planning. What's the best way to model such forecasting problems?
Okay, so that's a very good question. Let me just answer the general. So I won't talk. Let me answer the general question first. You're right. It's actually weather forecasts are best for T+7 and below, and that's really not because of AI. It's really because of numerical weather prediction, right? And it also depends on the parameter you're trying to forecast for. So, for example, let's say you're trying to forecast for wind speed or wave height, then of course your time horizon for accuracy is going to be smaller. But if you're trying to forecast for something which is more slowly varying, like temperature, and let's say temperature, let's say in the US or let's say Europe or China, then these mid-latitudes, the temperature changes are much slower. So therefore, you can actually extend the horizon well beyond 7 days ahead. You might even be able to extend to about 30 days ahead or 90 days ahead in some instances using statistical techniques or using AI, right? Now, to answer your question about voyage planning, 30 days ahead, the best answer I can give you is to use some combination of historical data plus selection of that historical data based on some AI techniques. But the problem is that the quality of data sets we have is very small because we only had weather satellites for weather prediction since about the 1970s. That gives you only about almost just 50 years of data to work with. That's not very much. Okay.
Okay. Ken, I think that's all the question we have for now. Okay. So we can continue then.
Okay, cool. So I will first describe something what I call the naive network. And the naive network is basically you take your past data. That means how beginners would normally do a forecast, right? So you take the past data, you shove it into your feed-forward network, and then you get the forecast. Okay. So this is a very simple setup. And it in some situations, it does produce good answers. But in a lot of situations, it doesn't give you a good answer. Okay. So let me explain why. Well, the first problem is that when you do it this way, your network has to learn which is T+0. Okay, so that's bad because the T+0, it means the latest value is very important. And you want to give as much information to your network as possible. So because you waste time learning T+0, a lot of your experiments will fail and you end up with a persistence type forecast if you're lucky. Okay. The second thing is that when you do this, your time series has to be detrended. In other words, let's say you've got, especially for like stock or functional data sets, right, where you've got these upward trends or downward trends, etc., right? So you need to detrend these things. Otherwise, you don't have enough examples to learn from. Okay, you have to detrend them. And it handles spikes and rare events very poorly, obviously because they are rare. And so it's hard for the network to learn these rare values and to cluster them accordingly. Okay. Now, I also want to talk about something called the prediction pipeline. So this is just for those of you who perhaps don't do a lot of forecasting. This is how we normally do stuff. You first have a prep stage, okay? And the idea is that you put all your normalization scripts, missing values, noise removals, or maybe you're trying to have some synthetic inputs like wavelets, etc., and so on. You put it in the prep stage. After that, it goes into a windowing stage where you have a windowing being done, or perhaps even feature engineering. Okay, so in this talk, I won't talk so much about feature engineering because that's a whole new thing. What I would just focus on is just taking a simple window and trying to work with that. Okay, but obviously you shouldn't do that, right? Okay, and finally, once we have that window data, it means it's chopped up. Okay, so in the prep stage, the data is still in the time series sequence. In the windowing stage, it is chopped up, and you've added some features, etc. And the training stage, you train your model. Okay, it's all about risk minimization at that stage. And then, of course, you start to do some kind of prediction, right? So most of the time, you'd spend actually in the least amount of time is in the prep stage because you want to just fix it once and for all. And today, we'll be talking about the training stage almost exclusively. Right, and we'll do a bit about the feature engineering as well, where usually you have a lot of changes. But today, because I'm introducing new concepts, we'll be doing more on the train stage and a bit on the feature engineering part. Okay. So in AutoCAD, we have it's a very similar mapping. You've got a prep script, and that goes into a windowing script called pre.m. I'm telling you this because I'll go through the system later on, so you can see it for yourself, and so you don't get it gives you a fixed point to think about. Okay, and then you've got the training, and the train stage is defined by two things: by a network and by a config. So the network is basically your network configuration, and your config is basically possibilities or settings that you can set for the network itself. And then of course you run the prediction. Okay. All right, all of this stuff is orchestrated by a single file called main.m. Okay, so we cleanly separate this stuff out because otherwise you get a mess. All right, so let me just demo now on AutoCAD the naive network so you can just take you through. Oops. Okay, I've already run because the first thing I'll do is I've got actually a few data sets here. A crude, which is for crude oil prices, which I won't do today. I'll focus just on the temperature data set. Okay. So let me just run this thing for the temperature data set. So the first thing you want to do, obviously, is to check out the stats that you have from this model itself. Okay. And I'll run the prep. And I find that the mean temperatures are around 27 on the training data set with an SD about 0.8 and a mean of about 28-ish and 0.7 for the test data set. What I'll do then is to just fix these numbers on the normalization, right? So this is Mojo on your left-hand screen here. So what this does is just to take that data minus, remember it's from left to right, so it's 28 minus 0.8 divide. So I'm just giving a mean of nearly 0 and an SD of about 1. Okay, and map just applies that to the entire column. Okay. Now, so once I'm happy with that, okay, I then want to calculate what is the 5 week persistence. So this is the T plus. So I've done a simple persistence calculation out here. Let me just run this again because I'm lazy. And so I get for the test data set, it's about 0.675. Okay, that's my persistence loss after it's being normalized, not before, but after. So that's why I put the persistence down here. Okay, so recall that persistence simply means that the forecast for t plus 5 is just the current value, the present value. Okay, and that error is 0.675. Okay, so what I want to do then is just to call up my notebook and save that value out here. Now I've already obviously keyed this stuff in so I don't mess things up, but you can see the value here is 0.675. Okay, so now let's just close this and we move on to training the network up. The naive network that is. I'm opening up main.m, config.m, pre.m, and network.m. So let's go through this one by one, right? So the pre.m is just where the windowing is done and the features are done. So in this case, I've selected there's only one column of data. If you look at the data set, let's say this one here. There's just one column of normalized data. These are normalized temperatures after the subtraction by the mean and the SD, right? And so I'm just selecting A5 here. Let me just blow this up for you. I'm just selecting A5 as my labels, and I want to get a window from A0 to A minus 20, in other words, 20 weeks back in the past as my feature. Okay, is this a raw window? Now, normally you wouldn't use raw windows, you use features, but I'm just using a raw window just for simplicity. Now, I've already set this network up for dropouts and everything else, and I've tuned it as best I can. Okay, so I've used a dropout of 0.1 on my main network, on my feed-forward network for all the layers. I've set the base layer, the first layer, to be a size 64. And the input size is 21 because I have 21 inputs from A0 to A minus 20, right? So that's 21 values. Okay. And I'm going to use the Adam solver. Okay. Use SGD only when there's a need for speed. Otherwise, Adam is good enough. I'm going to repeat the experiment 30 times. So typically for this kinds of forecasting and so etc., you don't want to just rely on one or two. 30 is a good number to get. So you get a feel of what kind of variability you have. The dropouts introduce, even with Adam and with maybe a Xavier initialization or even a constant initialization for your weights, the dropouts obviously would introduce a lot of variability in the results. Okay. Okay, so let's just run this. So the first step is for me to prepare the data set, to do the windowing itself, and to save it onto the server. So that's done. And then I'm going to train my models up or submit them for training. Okay, so I've got my 30 configurations all done, and I'll check for the status as it's being processed, right? So this is asynchronous, so you can go off, have a cup of coffee, and come back again. And it's fast because the data set is quite small. We only have about 1,000 plus values in total. Okay. Let's check the losses, and this is where it becomes interesting. Okay, so the losses don't look too good. So you can see that you're getting the models being trained, right? So the blue is the training loss. The red line is your test loss, and it's been stopped here because of early stopping. I've set the max ITERs to about 10,000, so that should be a problem. But I've got early stopping putting in, right? And these are my loss statistics for all the runs. These are all just repeats, so there's no need to go through them. But my lowest loss is 0.61, right? And that's not much better than persistence. So in fact, here it's 0.61, but I had a better value before. Okay. All right. So let's try and do the evaluation. That means we run a prediction this time to see, how is the model actually performing, etc. Right? This is asynchronous as well, so you need to test it out and see whether it's done. Okay, it's all done. Okay, so you see, because of early stopping, the model hasn't had a chance to train properly. So you can see it's actually the red lines are the predictions and the blue lines are the actuals. And the red lines haven't filled up, right? And you can see the blue lines are actually quite spiky. Okay, this is the test data set, and you can see it looks really bad. To be honest, a lot worse than persistence. Okay, and this actually beats persistence, yeah. Okay, that's a scatter plot for training, scatter plot for testing. It doesn't look too good. And this is the lag plot. Okay, so the lag plot is interesting. If you recall, you should see the peaks, right? So the blue one has got a single peak around 0. The training peak is 0. Okay, and that means it's actually learning the learning correctly. And here you've got really one minor peak here at around persistence. Well, this is about maybe lag 5, and the major peak is around 13. Okay, so what this tells you is that the lag for this is between, well, you've got two different lags, one at about 13 and only one around 5 or 6. Okay, not a good forecast at all. Okay, so that's that. So let me just close this down. Okay, we have a discussion now for about a couple of minutes. Cool, Peter?
Yeah, sure. I think we got two questions. So the first one is, additional features used other than time series data? So like, for instance, maybe a month, week, day, hour numbers, location, etc. Any potential leading indicators?
You have to be very, 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 very careful about how you introduce things which are monotonic. Like time, for example, is monotonic. Or things like which are cyclic, like the day number, for example, the day of the year, right? And why that is so, or day of the week, even worse. Okay, because you have the day of the week 0, 1, I say 1, 2, 3, 4, 5, 6, 7, and the next day is back to 1. So it's a discontinuity there between the 7 and the 1, although they are adjacent in time. Mm-hmm. Okay, so for things like time, obviously you're not going to use the date stamp. Okay, I hope you guys are not going to do that, right? So that's off the cards. But even when you have things like the day of the week or the day of the year, you have to be careful. I think day of the year might not be so bad, but I think day of the week is definitely, you don't want to do that, right? So one way around that is to use instead the angle, all right? So you think of it as a circle, okay? Then think of your 0, 1, 2, 3, 4, and so on, the day as an angle around the circle. And instead of having just one number as an input, which is cyclic, what you do is you instead put in a UV component when you're on the circle. So you have two inputs, okay? So that's how you handle things like a time. So the inputs, when it comes to things like time and so on, you have to be careful. Other inputs, comes like position and so on, I'll be very cautious about doing stuff like that. Okay, you really have to understand what you're trying to do before you just shove it in, or your network will be usually stuck in memorization. Okay, it just memorizes and it trains very well, but the other stuff is rubbish. Now, one way to eliminate stuff like that is to use perhaps pruning, or later on we'll see weight input scaling.
Okay. We have one more question. So the question is synthetic input in prep stage different from testing, training in training stage?
So the synthetic input is where you create some new input based on your domain knowledge, right? So oftentimes, let's say you got missing values, okay, and you want to have data imputation, right? So you might instead, let's say I've got station A, it's got some gaps in data, right? I got station B, which has got some other gaps. So I can then fuse these spatially to create a synthetic station, so to speak, which I can use. Another way to use synthetic inputs might be, for example, to run like a windowed Fourier transform or some kind of wavelet transform on a window or some other thing, right? And then from there, actually take the coefficients of those things as inputs. That's what I mean by synthetic inputs. So for this talk, I only have one column, but typically for the inputs, you have many columns, okay, as inputs. So you have column A, B, C, D, or column 1, 2, 3, 4, etc. But for simplicity, I'm going to use one column for this training example. So if I want, for example, if I'm trying to like forecast weather in Singapore, I wouldn't just do a single kind of what's called a weather data. I also include things like maybe the cloud cover. I'll include things like the temperatures elsewhere. I'll include things like wind speed. I'll include even the stuff like temperature in China, for example, or Indonesia, because those two things do affect weather in Singapore as well. So multiple columns typically.
Okay. Let me see whether there's more questions. No, we don't have. Okay. So I know you can continue.
Good questions. Keep them coming.
Oh, wait, hold on. There's one. Let me show this. Okay, can you elaborate a little on how you normalize your time series? Are all values relative to T naught, or would you use other baselines such as moving averages?
Okay, I think how you normalize it really is up to you as long as it makes sense. So normalization is, okay, so you have to understand what is the purpose of normalization. So if you're dealing with, let's say, if you're using, for example, let's say, I don't know, like a random forest, like XGBoost or something like that, then don't normalize, okay? Because XGBoost and those kind of decision trees, they don't care. But normalization is very important for neural networks. In fact, it's super important for neural networks. And so there are two reasons why you normalize. The first one is because if you're using a saturating, of course, since the neural networks have saturators, all right, if the numbers are too big, they will saturate straight away and you get rubbish. It won't learn quickly enough. Because once it saturates, the gradient along the tangent H, or let's say the ReLU on the back side of it, is zero or near zero. And so because your gradient descent and backprop depend on the gradient of your activation function, because you're already hitting near zero, you won't get any learning at all. Okay, so you want to make the numbers small. The other second thing about normalization is that the inputs need to be about the same size. Okay, because if you have one which is a bigger size, because you can adopt product, right? If it's a big number, let's say 10 times, 20 times bigger than the rest, it will dominate the rest of those numbers and swamp them out. Okay, so that's no good as well. So you want to actually make sure that they all normalize at the start. So what the normalization you do, all you need to make sure is that it's the same normalization that you use for your training, for your testing, and for your deployment. Because otherwise, you'd get you need a different model, you see, because your model, let's say you got a stationary time series, okay, for the training and for the testing. If I use one normalization for my training and a different one for my testing, obviously, my learning will be very good, right? Because it's different, right?
Yeah. Okay. Ken, I think let's continue then.
Okay, good. All right, so now I want to introduce to you the first trick or the first innovation, and it's called a difference network. Now, the tricks I'm going to teach you, they are not foolproof. Neural networks are very fussy, okay? You need a lot of experience before you can really start to get results. So a lot of people give up. I know a lot of people say, look, neural networks are not for me. I may use some XGBoost or some stuff like that. And that's probably true. I think for casual problems and so on, the XGBoost and tree-based systems are idiot-proof, and they allow you to focus more on the data manipulation part, etc., right? But neural networks will give you the bang for your buck, honestly, when it comes to forecasting, because oftentimes you get a better lag, a lower lag compared to decision trees. Okay, and there's a lot of knobs and tricks that you can use to actually hammer your network so that it gives you a good result. So the first trick I'm going to teach you is called the difference network. So this is the first thing you can do. And the idea is that you got your past data, but you take out the y naught, the y t plus 0, right? And this, by y, I mean the label you're trying to forecast for, but at t plus 0. Okay, you don't include it in as input necessarily, okay? Or at least you separate it out. Okay, so then what you have is you have your past data and you pass it through your feed-forward network as usual, but you add the output of your network with the y naught, okay? And this becomes your forecast. All right, and this simple change can actually make a big difference for a lot of problems. Certainly, we have seen a lot of improvement in anything with cyclic, like demand forecasting, etc., or where the input data isn't so noisy. This is actually just a fantastic job. Just this one change alone. Okay, so why? Because it oftentimes gets you a network that almost instantly beats persistence. So just now, the naive network happened to beat persistence as well, but it's by no means guaranteed, believe me, okay? There's also very little need. I wouldn't say no need for detrend. I would say little need for detrending because you're taking differences. So even if you go up by constant value, for example, then there's no need to really detrend. Spikes are okay, all right, because they are transitory as well, and you're looking at the differences, which are much smaller than the spikes. And because you are forecasting dy rather than the y value itself, you typically get more labels, more examples that the network can learn from. And that's the reason really why we want to use this. There's just so many good things, okay? So I'll give a demo of the difference network. I won't run it through this time. I'll just give you the results so you can see it for yourself. I'll do this. Okay. So that was our network for the naive one. So I've already actually trained this model up for you. So instead of wasting time, I'll just look at the loss graphs. Oops. Need to open up the main. So this is the difference network. Okay. All right. So if you recall, you see at least there is some learning here in the first part before it starts to flatline and then it gets chopped off by early stopping, right? So this part here brings that error rate down to, I think, 0.49, okay, which is actually pretty good. It's not too well, it's not too shabby. It's much lower than persistence. Okay, and all we did was just to add that term on your network. Okay. Right, so we add the y naught here to the output of the network before we compare it against the y, and the Euclidean loss is just RMSE. Okay. All right, and as my input, what I did was I did a difference. So I have the A5, which is my labels, 5 weeks ahead. I have my y naught here. I selected y naught as the second column. Okay. And I've added, I've got those 20 columns, but I take a difference. Okay, so difference, I've set it up to be 5 steps. In other words, T0 minus T5, T1 minus T6, etc., and so on. Okay, that's how I do the difference. Okay, that's it. All right, and you can see that the results I get are actually pretty good, right? So previously the naive was 0.57. When I did it on live just now, I got 0.61, and now the difference gives me 0.49, which is actually a substantial improvement. Okay, and if I go to my predictions, let's just see what happens here. Okay, you can see also that the training is a bit better. It's a bit fuller than before. And the forecast is also a lot better, or at least it looks like it, okay, visually. that's for testing. This is for this is for training, and this is for testing. Let me just shrink this down a bit. Okay, now this lag graph tells the truth. So you've got a peak here at t+0. The blue is for training and the red for testing. I've got a peak here at t+0 for the train, a major peak. But I'm also getting a minor peak at the t+5. Okay, and that's really because I'm using dropouts. So the more dropouts you use, you'd find that your training becomes your training peak becomes lower and lower, less overtrained, and it reverts to the Y0, which this blue line goes, the blue peak goes up at persistence. Now my test, unfortunately, is still very peaky at persistence, t+5. Okay, but I'm beginning to see some semblance of a hump here. You can see it, okay, at a t+0. Okay, and our goal really is to try and grow this peak while keeping the RMSE down, and let's see if we can do that. Okay. Okay. All right. My second trick is to use something called momentum and force as inputs. In other words, I want to just have the first and second order differences of all the inputs as new input into the model itself. So the idea is that by putting the first and second order differences, you can detect movement and rate of change, and you can actually cluster a lot better. And this also happens to help to reduce lag. You have to use both first and second order differences and not just the momentum alone. All right. So I define them quite simply. I don't, because my data is normalized and I know the differences are okay. So the momentum is just the x at some time t minus the x at t minus h, where h is your lead time. And the similar for force. It's just the second order difference. Okay, some people like to divide by the x's. I feel that introduces or creates outliers, especially if your x's are small or near 0. Okay. All right, so let's just look at the results of doing something like this. Let me just close this up. And go to your force. So I've got my network, my pre. So the network remains the same. I've not made any changes at all. It's again the okay. I didn't talk about the network just now, so let me just go through it very briefly. So this part here is the training part, and it does the training. I've got two inputs. The training data and the testing data. Column 1 is my y, column 2 is my y0, and 3 onwards, this is variable, would be my inputs xs into the model itself. I'm actually shoving this into a network function, and the network function has got 1, 2, 3, 4 layers. So I've used a 4-layer network with one linear combiner with one output here at the top. I'm sure you guys can see this or not. It's a bit small. Okay. All right. So it's got one output at the top, and I'm being quite gentle. I'm using a 2/3 shrinking at each level. If you shrink too aggressively, sometimes that causes it not to train well. Okay. And for my perceptrons, I've defined them as an inner product, which includes a bias, and a ReLU as my saturator. And I've got the dropout layers defined as well. This dropout probability is defined in my config. All right, so I've used 0.1, 10% dropouts. Okay, now I've started an NN size, that means the bottom layer here on the network. This NN size here, this is the bottom layer of the network, this is the top layer of the network, is 64. Okay, so a large-ish, this is actually considered large for, I know for image processing, you use much bigger networks. But for forecasting, you typically use smaller size networks, and you use dropouts pretty heavily, right? So, okay, my input size has changed. This number here is now 33. I've just done a calculation just to make things go right. So, this is my inputs. I've got my A5, which is my labels. This is my Y0, okay, and then here I've made the difference as inputs. Then I've used X. I've used just the basic differences, and I've used the momentum and the force. All right, so they're just defined accordingly. Okay, nothing too fancy. All right, so let's look at the losses that we get from this. Okay, they look a little better. Okay, so previously, you recall, there was some learning here in the flat line, but now that learning has extended by quite a bit, and you've gone further. Okay, a lot of the variability here is just caused by the dropouts. Okay, and my minima, the minimum value is 0.45, right? You'd also want to pay attention to how far that minimum value is from your mean. So I also want to just display the mean minus min over the SD, right? To just show you how much of an outlier is that. Okay, so ideally you want this number to be smaller so that it's more likely, more probable for you to get a good answer. If this number is too big, it means that you have to it's an unlikely value. It's quite far away from the mean of your tests. These are all just 30 repeats, right? Okay. Now let's look at the predictions from this thing. Let's see if it's improved things or not. Okay, so again, this looks not too bad. It's fooled out. It's also it's missing the peaks though on the training side. All right, so but on the test side, you can see it's not too bad. It's forecast here correctly. There's some lag here for the minima, but it's got the general trend correct. But this part here is a bit laggy, and I think this contributes a lot to the lag, right? This part here. The problem is that this test data set is too short. I think 64 values is already way too short. You want to run something that's bigger. I purposely used a small data set because to make it feasible to run this and to run a lot of experiments. Otherwise, it take a lot of time. Okay, so let's look at the lag graphs. So look at the lag graphs now. Okay, so here you see what's typical. You've got a peak around 0 for the training, but you have this peak for the training as well. That's only because we've used dropouts, and the peak for your what is it called test remains high, but you have now a distinct peak here at 0, right? So this is what we're trying to encourage, and we're trying to build up as we go. Now, it may not be possible in this scenario, in this case, to make this really good because we're only using one input, which is the time series data itself, right? To be really predictive, there's only so much that history from your current measurements can tell you. To be predictive, you want to look at other variables or perhaps data collected from a different location, especially if you're dealing with spatial data like weather data or perhaps even demand data and so on, right? Because that can also be spatially correlated, right? So, for example, let's say you've got you're trying to forecast demand for energy demand in the US. Okay, let's say your results, your station is somewhere in I don't know, let's say Florida. Okay, and if your data is just in Florida, you won't get a good prediction. But if you include, let's say, data points, let's say for temperature, etc., further towards the west, because the weather always comes in from the west, then you get additional data which can actually make this go right down and this go right up. Okay. So we have also like we ran in fact a competition this was late last year, December last year, before COVID broke out, and we wrapped up in January, where the contestants actually try to forecast dengue in Singapore, and they use a lot of weather stations in Singapore plus the dengue cases, not just the dengue data alone. Okay, so that's that. So let's look at the scoreboard always. So the difference got us 0.49. This gives us 0.45. Now, obviously, these numbers will change. The question is, how likely is it to change? So if you have the momentum and force, generally speaking, you will definitely get a better result. Okay. Okay, the next big trick I want to introduce is something called an input scaling subnet. And the idea is twofold. There are two problems right now that we have with the inputs. The first is that unimportant input can slow learning. So especially you have, let's say, a large network, for example, right? A large input vector, then a lot of rubbish in there can actually slow down learning. Obviously, to do this thoroughly, you have things like input pruning and so on. But before you do input pruning, you need to know which inputs are important and which are not for the network itself. You can't just take, let's say, something from XGBoost and then try to implement those ideas here in the neural networks, because they could be exploiting different parts of the data, so it might not translate. Okay. Now, worse, if you have noise, for example, that becomes learned by the network. That's not good, right? So we need a quick way for gradient descent / backprop to just kill these off as early as possible. Okay. But if you rely on the bottom layer of the fully connected net to do it, then each fully connected net has got n weights which need to be adjusted, right? Because each element of the input vector gets sent n times. So if my input, let's say base layer 64, I got to make sure I'm zeroing 64 different numbers before I can just shut down that input so it doesn't make too much of a problem. So in practice, this rarely happens. Okay, it's too hard and too slow. Now, the second problem, and this is, I think, one that's more important for things like financial time series, like we discussed earlier on in this talk, is that outliers can dominate batch learning. So it's still possible to have outliers even after you do this kind of stuff, and they can actually still dominate your batch learning. Okay, if you do a subtract with the mean and divide by the SD, there's no guarantee that you're limiting. Outliers will still be there, obviously. Okay, and they can just wreck your learning. Okay, so you want a way to just automatically reduce the outliers without making too much assumptions about their PDF and that kind of stuff, right? It's very fussy. So the simplest way to do this, the poor man's way of doing it, is called input scaling. All right. So the idea is very simple. You've got an input vector x1 to xn. This is the vector elements. Okay, not different vectors, the vector elements. Okay, so this is one input vector, and you pass it on to a scaling layer q1 to qn. So these are simply numbers that weights that you need to learn. Okay, and this solves your first problem of trying to kill stuff off. And then there's a second problem, which is trying to squash these outliers, and you can just simply use a 10H. Okay, you have to use 10H and not ReLU and some other stuff like that, because 10H is symmetric, and your outliers could be either very large or very small. I mean, very negative or very positive. Okay, so that's the basic idea. Then this is what you use really as your input into the network, into your upper main feed-forward network. Okay. So you have just a queue. It's a cross product with your old x, and this is your new x. And typically you have a squashing function. Now you must constrain your queues to be bigger than 0. Otherwise you get problems. And later on, we'll replace the 10H with something that's more fancier to actually do this kind of stuff. And that's a compression decompression subnet. That's trick number 4. Okay, but for now, let's just use 10H. Okay, so I've done this again in AutoCAD. And rather than running the whole thing again, I'll just show you my results. And I've not made any changes to pre, and I think no changes to the config, right? Okay. All right, so I made one change to config, and that is that I'm deciding here whether I want to, can you see this? Whether you want to run that 10H or not, okay? And I think the result that I got was that we want to clamp. We do want to clamp. So let me just show you what that means. So here is my network again. So I'm just introducing the scaling function. Remember, Mojo is left to right, top to bottom, right? So whatever is first is run first, whatever is second is run second, whether it's left to right or top to bottom. So the scaling is run first as my first layer, and then the Septron layers come after that, and followed by the final LC, right? So this is my main network here, and this one here is just my input scaling subnet. And it's just a diagonal matrix I'm trying to learn, okay? And depending on my config, clamp on scale, I can decide whether to put, this is an if, it's a conditional, if, so like an end if. I can decide whether to put the 10H layer or not, okay? And when I do the losses, okay, you really do see a slight improvement, 0.45, right? But it's still quite, so this number here it's a bit too large for comfort. I think anything above, but it's not too bad. I think it's, when you get like 3 and so on, I think that's when it's, you got, you know, it's probably fluke. But 0.25 means it's probably going to be reproducible, but I prefer something which is something like, you know, 2 and below. Okay, I can just order this. These are all the same copies. Oh, no. So there would be 2 different kinds of configurations run here, right? There's one where it's clamped and the other one where it's unclamped, and it looks like the unclamped wins by a small, sorry, not this one. So the clamped wins by a large margin. So you got one clamped, which is true. Here one config false, and then true, then false. And so the falses are pretty much higher, right? So it's more likely that if you clamp it, that you get a better result, and that's not surprising. That's because clamping just reduces any kind of outliers, right? Okay, and let's just check the losses again. The losses is 0.45, and that's 2. And that's slightly better than the one that you got from Momentum Enforce loan, right? And this is something that's quite normal in neural networks, or in fact, I think in generally speaking, is that it's diminishing returns. Each thing that you do extra gives you less and less value. And I think we are actually juicing as much as we can from the accuracy of these models because we're just using one input. So now I think slowly we're coming to see that the bottleneck is slowly becoming the fact that we only use one input, which we wouldn't do normally. Okay, let's look at the predictions. Okay, they're not too bad. They're all fooled up. Okay, and you can see here that is a lot closer. Remember, this is actually a 5-week ahead forecast. For comparison, from here to here is about 7 weeks. All right, so that's 7 weeks. Each tick here on the bottom is 7 weeks. So this looks like it's almost on the money. Okay, let's check the loss graphs, the lag graphs, and here you can see that this primary peak, although it's still at the red one is still at persistence at t+5, it's much lower than it was previously, and this has become much higher, although it's more spread out, which is no good. Okay, it's much higher than it was before, so that's a good thing. Okay, one of the problems we're having right now also here is that this time series is very long and this one is very short. This is only just I think 1.5 cycles, 1.5 years, whereas this is many years of data. Okay, which is something you probably face also when you do your own forecasting as well. All right, so that's that. Why don't we just break for a short discussion now? I'm sure you've got questions.
We do have one question, and it's related to COVID-19 predictions. So let me just show this. So any advice to forecast COVID-19 cases, confirmed cases, and fatal cases by country to see when it will end? So I did a naive model using LSTM sequential model for the next week and would like to improve. Yeah.
Okay, where do I start for this question? Okay, it's a good question because I think it's an honest question, right?
Yes.
I like that question. But there are a lot of the question itself tells me a lot of misunderstandings about forecasting. Forecasting is not magic, and these neural networks are certainly not magic. Okay. I think that there are two issues here when it comes to forecasting, right? The first one is that all forecasts are driven by data. And so if your data is rubbish, you will produce rubbish as well. Okay, it's just normal, right? So the problem that we have when it comes to COVID is that the testing that is done is uneven. Different countries have got different kinds of testing regimes, different kind of testing penetrations, etc. Right? And no matter how good your testing is, you can only test so much in a day. So you don't really know when or how many cases out there, and you don't know how fast. You don't know how many cases out there, and you don't know a lot of different things. The other thing is that it's a moving target as well, because there are many things that your data can't capture, like how well is social distancing happening, right? You're not capturing things like temperature of the different countries, right? Which we really need for a forecast. When COVID first came out, now I was quite struck that where you get high infection rates, China, Iran, and Italy, for example, right, where it spread very fast. Of course, there were a lot of other factors involved. One of the common things that were there also was weather, where it was all them dry climates at that point in time because it's winter, and a temperature between, I think, 10 to 12 Celsius, right? So as the weather changes, obviously you get different changes as well. And humidity has been known also to prevent viruses from spreading. So there's so many factors out there which are not captured in models that just look at the data. Plus, the data itself is very questionable, okay, in terms of even if they report it honestly, whether report it on time, whether there's bias in the reporting itself, okay. Don't neglect when it comes to things like healthcare and so on. You gotta be very suspicious of the data. You have to be suspicious of healthcare data because there's money involved. For example, if you look at the cases in New York, you find the death rate attributed to COVID is very high. But if you look at the death rate elsewhere around the US or even in Europe, etc., and so on, the death rates are much lower, right? And that could be because in New York, people are I think the governor, I think he gave money for, I think if you are recording these victims, etc. Right? So I'm not sure about the details, but the thing is that there's also money involved, right? So reporting could be biased or skewed. So the first part of my warning to the person who asked this question is that it's a good question, but the data is very suspect. Okay. So the second part is that is the process modelable or not? All right. So I think I've answered a bit about that, and that is that there are other things in the model that you need to introduce which you don't know. Okay. That's the second thing. The third thing is that do you really need to use a network like LSTM? Right, so LSTMs are hard to train, and if you don't know what you're doing, you can easily burn yourself. Okay, so even with a simple setup like this, so I purposely did today simple because it's reproducible and you can really extract a lot of insights. But when you introduce things like memory in your models, where it's stateful, then becomes a lot harder to debug and a lot harder to understand. You can't just shove it in and expect to get a good result. Okay. Right.
Okay. Any questions? We just wait for one more, see whether there's any more. Nope, we don't have. Okay. Arnold, you can continue then.
Okay. So I've got a couple more tricks to show you. I'll probably do a couple more. Okay, so this trick is all about dimensional reduction. Okay. So the first point is that neural networks really don't work well with large dimensional inputs. Okay, so in fact they're happier. Maybe the reverse is that if your inputs are larger than 100 in size, then you've got to worry about dimensional, what's it called, the curse of dimensionality. I'm sure you've heard of that before, right? But frankly speaking, neural networks like this are better off when your dimensions are smaller. So the idea here is that you want to reduce the dimensions of your input vector using some kind of compression, decompression subnet. Okay. So I'll explain what that means. You have your inputs, you have this compression, so it narrows down, and then it decompresses, so it goes up. Okay. And you want to train the network so that your X reconstructed must match your input X, obviously, but you don't use the reconstructed vector. Instead, you tap the center part of the network, the reduced vector, and you use that instead as your input into your feed-forward network. Okay, so this is a distinct subnet that you use just to reduce the dimensions of your data. Okay. Now, in our case, if you recall, we have, I think, 33 inputs. Okay, that's the difference plus the momentum, and then the force. All of that is just 33. So it's not a big dimensional vector, but even then, you can actually see some improvements if you do some dimensional reduction. Okay, but it's tricky, and you need to know how to do it correctly. Okay. So the first thing is this: keep it simple. Is that 3 layers is more than enough. Okay. So don't go crazy and try to use multiple layers. 3 layers is more than enough. Okay. And use 10H because it saturates at both ends, and you want that. And the compression factor, in other words, from the base to the middle part, how much should you compress? Well, you can start with 2, or you can start to scan. You can scan a few different numbers and see which gives you a good result. Okay. And you can actually easily, for most time series, you can just train these models up. In fact, you probably want to train them up simultaneously with the rest of your network with a separate loss, obviously. Okay. All right. So I'm going to show you how to do this. This is a little more complicated, but not that hard. And I think this example also shows interactions between different things. These techniques are not all independent of each other. They actually do have interactions, and you have to be just a bit more careful about how they interact, right? So let me open up the config. Okay. The main. The pre is all the same. I'm not changed the pre at all in my network. Okay. So you can see here, my network now is starting to grow. Okay. Right, so this is the main part of my network, right? The network word itself. Now, I previously had just the scaling followed by the 4 layers and then the final LC layer. Now I'm introducing the bottleneck just after scaling. So it's scaling first and then bottleneck second, okay? So remember, in Mojo, everything is in order. So this is why, well, it matches what you would think of as a transformation. Whereas in Python, or let's say in Java, it will be bottleneck bracket scaling, not like this, right? Okay, so you do the scaling first, and then you do the bottleneck. Okay. Now, my main network, the perceptrons are ReLU-based, and they have a dropout. Previously, I used a dropout of 0.1, but now the dropouts need to change, and I explain why in shortly. Now, my scaling before had that diagonal thing, but it also had a 10H. Now, I've removed the 10H because the bottleneck already has a 10H. Okay? So I don't use a 10H here and saturate too early. I've removed that, and it's up here right now. Right? And this is my dimensional reduction subnet. The perceptrons now are 10H based, so it's just the inner product with a 10H after that, okay? And this needs a little explanation. So I've got the input that comes in from the bottleneck, so this is the input. Anything in purple that you see here is a comment, okay? So this is not, this part here is not a method signature, this is just a comment for me to know what the inputs are and what the outputs are, okay? This is a binding which accepts it, which calls the input to bottleneck as XS, which is the input layer. And here, what I'm doing is that I'm creating the first part of the bottleneck, okay, the base layer. Then here I'm doing the second. So you probably can't see this if I highlight it, but let me make it bigger. Move this off. Okay. So here, it's again a layer of perceptrons, but the size is the input layer divided by the bottleneck size. Now, the bottleneck size I've used is actually 4. What I did previously was to scan a few different values. So in AutoCAD, sorry, you can actually scan stuff by giving them multiple values. So in this case, the bottleneck could be 1.5, 2, 4, or 8. Now, to save you the trouble of doing all that stuff, I've done it already. And the best answer, at least for this configuration, is size 4. Now, this will definitely vary or be different according to your application. So you must scan the appropriate size for your bottleneck so that it's not too small and not too wide. Too wide, you lose the benefits of the bottleneck. Too small, then it doesn't train properly because you lost too much information, right? Okay. Now, the dropouts also need to change. Why? Because previously, for all the previous experiments, my dropout was 0.1. And that's because previously, the size of my inputs was 33. Now, the size of my inputs is 4 times smaller than that. So it's roughly about 10-ish. Okay. So it's much smaller than before. And so because of that, I've got a lot of neurons which I don't need anymore. I need to cause dropout. Otherwise, I get over training. Okay, overfitting. So when you use a bottleneck, be sure to actually also scan for a good dropout. Now, this should be obvious. Which direction you should go should be obvious. It should become larger. And how much larger is really the question. Okay. And I've also increased my repeats to 60 because the more of these techniques you use, the more unlikely it is for you to get a good result. So you need to work a bit harder. So I've only just doubled the amount of tries. Okay, so let's look at the losses. Okay, so you can see there's a lot of variation here, and because that's the bottleneck is introducing a lot more fuzz into your training, a lot more variability in your training, right? And also because of the dropouts have increased. So previously, when the dropouts are lower, you get a narrower band. When dropouts are higher, obviously you get a wider, higher band for your training, right? And you can see some do well and they're obscured by the blue, so you can't really see it so clearly. And of course, a lot of them will just fail. In fact, your main body is not doing too well here. It's all the way up there. Okay. Now, this is the losses not for the main network, but for the reconstruction network. So you need to check this graph to make sure that it's actually nice and smooth and going down. So now here, I've got my blues higher than my reds, which might seem unusual, but not really, because my blue, my training data set is very large. And obviously what this means is that the input data set can be easily reconstructed. Okay, so you want to see this going down, but you see there will always be a small amount of error, reconstruction error, and this is what you pay for when you use a bottleneck layer. Now, because this is such a mess, and you can't see the all 60 configs, there's too many of them, and they're obscured by the blue here. I've just plotted out just the best config here, and so the best config here, this is a good result, right? So you've got, your blues going out there, and you've got your red line there, and it's actually reduced below. And let's see the how far you are from the main body. Not too far. 2.2 is not that bad, or 2.3 really is not that bad. Okay, which means that this result, if you work a bit harder, you might be able to reproduce it. Okay, so this tells us that using the bottleneck is good, but we only want to eyeball the predictions just to make sure, and to look at the lag plots. Okay, so here you can see, if you notice carefully, there's a slight shift towards the right. So it looks like it's a bit laggy, the training part, and that's natural because you've doubled the dropout values from 0.1 to 0.2. So typically what happens is that when you increase the dropouts, the training error goes up, but the test error goes down. Okay, up to a certain point, obviously, right? When they start to meet, then both start to go up. Okay, because that's just too much noise in the training itself. So here you can see, yeah, it's a lot better than before. It's really faithfully followed this thing down. It's actually easily forecasting this. There's a lot of oscillations that's to be expected. And then you've got the spike here modeled correctly, this trough here correctly as well. Not a bad result all in all. Okay. And the lags, well, it doesn't tell you a great story, but because this is such a short test sample, I would actually be a little skeptical of this, because that's why I need to eyeball this thing a bit more. Okay, so if your data sets are longer, then trust the graphs like this, like these lag graphs. They are much better at actually looking at that and giving you the information you need. Okay, but here, even so, we've got at least some semblance of peak out here, I guess. Okay, so that's the bottleneck, which is just for dimensional reduction. Now, I'm going to cover one last trick. Actually, I've got one additional one, but maybe we don't have the time for it. But let's just do this last trick. Now, this one I think is where it's contentious. Sometimes it works, sometimes it doesn't work. Not all the tricks I'm teaching you work all the time, and there will always be interplay or interactions between the different tricks. Okay, so like in this case, for example, in the network itself set up with a bottleneck, here I have an inner product layer, so my final LC layer on the final one, because I don't have a thresholding on the scaling layer, right? So my scaling layer is not thresholded. That means it's not a 10H. It's just scale, all right? Which means you can vary quite a bit even with the scaling, right, done. And I need to have the inner product or the LC layer to compensate for that. Now, when I use, in the second example, using the squared inputs, I'm going to start this shortly, this will change. So this is what I mean by interactions between these different tricks. You need to know what you're doing, okay? So it's a very simple thing. The first equation is just your normal, your normal input, right? So you've got some a dot product, and then you get a saturator, and that's your Y for your neurons, right? But sometimes when you have an X squared, that can give you the benefits of both perceptrons and more different networks called the RBF, or radial basis functions networks. Okay, this trick doesn't work all the time, and it's fussy to use in my experience, but I'll teach it to you anyway, so you can just play around with it also. Okay, and the idea is this, that perceptrons have got some set of benefits. They are less problematic when it comes to a large dimensional input. I'm saying large, but let's say around 100, but they are slower to train. RBF networks are fussier to train because they need smaller dimensional inputs, but they train well and quickly. Okay, so the idea is that if we can square the inputs before we feed our network, we can perhaps gain some or see some benefits. Okay, that's the theory at least. Let's try, or hypothesis, I would say. I wouldn't call it a theory, I'll call it a hypothesis, because none of this stuff is really proven mathematically. Okay, it's more experiential. Okay, so let's go back here. So I've got my dimensional reduction subnet, and this time I've commented out the final LC layer, and I'll explain why shortly. And that's because here I've changed my main network. I first scale, and then I add the squares to the squaring function here before I go to the bottleneck, right? So my squaring function, what I've chosen to do is to use the 10H to actually flatten it before I feed it into the main network. In fact, before I feed it into the bottle network. If you do that, if this is already 10H, then you don't need the inner product anymore. But if this were not 10H, like that, then obviously you need to put this in because you want this to scale properly. Because otherwise, this is already 10H. It cannot match something that has not been flattened. Okay. So I'm doing the reverse, which is this, and I'm flattening it out here. Okay. And I'm obviously, as usual, reporting the loss separately as well. So now the losses. Okay, so this looks terrible, and it probably is. What it tells you is that, okay, this is not a, okay, so what's happening here is this, okay? The stuff that you see down here, the blues down here, they are being overtrained because you can see the losses are very small, 0.29. So far, one of our better losses is 0.45, okay? And for each of these guys, you're getting all these upward test arrows because it's obviously overtrained. So you get a symmetric, flip up by the test losses. But for a few around this range, you're getting some training, and you're getting that kind of balance between training and learning. Now, what you notice immediately is that, and of course, the reconstruction is not too bad. Okay, it's doing pretty well. But the errors are quite big. Look at this error out here. So this is the blue is the training error, and the red is the test error. Okay, and early stopping is cropping it off quite early at just 850 cycles, iterations. All right, and the error here is pretty large, 0.54. Okay, which is even worse than what we had done before. But if we look at the predictions, we come to understand why the error is big. Oh, shucks. I think I didn't train this up properly. Sorry, guys. I'll just run the training here just from the start. We were fiddling with the backend just now. I think my colleague must have scrapped it out. So anyway, this will take some time. But instead of doing that, what happens is this. When you have these squares put in, what you'll notice is that the predictions will start to fluctuate. You get oscillations. And you do get improvement with the lags, but at the same time, you get these oscillations. And the oscillations are what cause the training losses, so the test losses to go up. Okay? So this is more of an advanced technique, and you need to be very careful using it, and you need to play around with it to get the right values. Also, what I noticed also using this technique is that the optimum numbers for the config, etc., changes. So previously we had 4 and 0.2, but when you introduce the squares, the bottleneck size that you can take, it's happy with, is much lower. Okay, so we have 30. Previously we had 33 and we reduced it to below 10, and now we've got 33 and it's just 15. Okay, and I needed to use more aggressive dropouts as well, because these were becoming it's a bigger vector. Sorry, I'm going to bigger vector because that was necessary for the thing to work. Okay, all right. I think I'll stop here. Any questions?
All right. So yes, any questions, anyone? Maybe let's return to one of the questions that was asked.
Yep.
Whether can you explain a bit more about the persistence that you were talking about through the talk? Can you share a bit more on the persistence, the definition, or maybe even the details a bit more?
Okay, so persistence is just a simple, trivial forecast. It's a benchmark, a brainless benchmark. Okay.
Mm-hmm.
So what it's a forecast. So let's say, for example, you got let's talk about, I'm a stockbroker. Okay, and let's say you're my client, and Ku says to me, Arnold, can you give me a forecast for the stock? Let's say Google stock, I don't know, 1 month from now. Okay, I said sure. The answer is I check the value today, and I tell him today. So what's the price of Google stock today? Let's say it's $100 or $200 or $1,000, whatever it is, right? I say it's $1,000, right? And that's my forecast. No matter what you ask me, I say it's the current value. So tomorrow you ask me again, I will say it's tomorrow's value, right?
Okay.
So that's a persistence forecast. So it's very much used in a lot of forecasting because it's simple. Okay. Number two, it is actually hard to beat for short lead times. So, for example, this is true for things like temperature. For temperature forecast, let's say we're talking about what is the forecast for temperature for tomorrow, and I give you today's value, you'd find that very hard to beat. Very hard to beat indeed. Okay. And if you did, it means that your model is really doing something behind the scenes which you're not seeing. And short lead times are important for things like dynamic demand pricing or demand forecasting. Like let's say you're in Grab or Gojek, I guess. You're trying to dynamically price your rides, right? And therefore you need to actually forecast the demands for your rides based on historical data plus current conditions, etc. Right? So the pricing time horizon is very short, usually about 30 minutes. or 15 minutes, maybe about 30 minutes ahead of time. Okay, so the forecast 30 minutes ahead of time, persistence is usually quite hard to beat. Okay, it's very noisy for these kinds of things, and persistence is not a bad gauge. Of course, if the time horizon shifts, let's say to tomorrow, for demand forecasting, something that's very, very fluctuating, then of course persistence will be very easy to beat. Does that answer your question?
Yeah, I think should be sort of the audience question. Any questions from the audience? We just wait for maybe a few seconds. So, no, we have more questions coming in. No, I guess not. I think that's all the questions that they have from the audience. But anyway, so yeah, no more questions. Hold on.
Okay.
Yeah. Okay. Anyway, let's. Okay. So anyway, I think that's already. No more questions from the crowd. So thank you very much, Arnold, for sharing your tips and tricks on using neural network for forecasting. So I think with that being said, I think that should be all already. So thank you very much, Arnold. Thank you. Thanks for appearing.
For inviting me.
No problem. Thanks for appearing on our first virtual meetup. I think that will be accolade for you. Okay. So for the rest of the guys, right? Just to let you know, I think our next meetup, the next virtual meetup that we're planning, right, will be on the 21st of. Oops, my spelling mistake. Will be on the 21st of May. So do check out the details from our Facebook page. Oh, okay. Yeah. So with that being said, I think thank you very much, everyone. Thank you, Arnold, once again for appearing on our virtual meetup. I actually learned a lot from you on forecasting as well. New terms. I'm going to go to Google and search for all these terms then. Okay. Thanks. So with that being said, good evening, everyone. So thank you very much, and have a good long weekend. Okay, thank you.
Bye, guys.
Bye-bye.